what we can do now is create something called as a learning rule. So learning, let's use a different color again. So we'll call this a unified learning rule. So what we saw previously is that if p was equal to 1 and a was equal to 0, then the way we updated our w and the way we calculated our new w was we took the old w and then added the value of p to it. Likewise, if we had the target as 0 and we got the value of a as 1, then to move the decision boundary, the way we calculate that the new w is we took the old w and we subtracted the value of p. And if in case where the value of target was equal to the value of a that we calculated, then we simply didn't do anything. We just said that, well, this is the final w we have, and so the new w would be the same as the old w. And in this all of these cases, the way we can formalize this is uh, we can say we can say here is that E, which is the perceptron error E is equal to T minus A, where T is the target that is given to us, the correct ground truth class for that data point, and A is what the network calculates in that iteration. So what we can do is we can write these rules in terms of E as follows. We can say that if E is equal to 1, and when E is going to be equal to 1, that is going to be equal to 1 when T is equal to 0. So if E is equal to T minus A, right? T minus A, if T is 1, A is 0, then we get E is equal to 1, and that's what this is. If E is equal to 1, then the new W that we calculate is going to be the old W that we have plus the value of P. Likewise, if the value of E is equal to minus 1, that is when we try and calculate E is equal to T minus A, where the T is 0, A is minus A is 1, and we get minus 1 there. Then the new value of W is equal to the old value of W, and in this case we subtract the value of P. And finally, if there is no error, if E is equal to 0, then we stop there and we simply say that the new value of W is equal to the old value of W that we already have, and no further updates to the weight matrix are required. And this particular part we can also write it as follows. So we can write the new W is equal to the old W plus E times P. What we mean by that is the old W plus T minus A times P. So that is how we update our weight matrix in each iteration when we train a perceptron. And just like this, we can also update the value for B. So for this we say B new is equal to the old B, and here we are simply going to change the sign of the bias based on the value that we have for E. With this, then why not look at yet another example. This time we'll look at a 3D example where we have two data points, and we'll start out with a random value for W and see if we can get the correct value for the W. And the data points this time that we are going to use are as follows. We have the first data point P1, that is equal to 1 minus 1 minus 1, and the correct target class for that is T1 is equal to 0. And then we have another data point P2, that is equal to 1 1 minus 1, and T2 is equal to again 1. So that is what we get. If we try to plot these, this is how we plot it. And before we look at the plot, let's also see what values we have for W. So W, we are going to use W value of 0.5 minus 1 minus 0.5, because three values, because we are in 3D this time, and the value for bias B is simply 0.5. We put all of this together. Here is what we see, that this blue dot is our P2, red dot is our P1, and the gray dot is the value for W1 that we just created, which is 0.5 minus 1 minus 0.5. And based on that, if we draw a plane, the hyperplane, to separate these two data points, the red and blue, we see that it does not do a good job um, based on the decision boundary created by the weight W1 that we have randomly selected. And so, of course, we need to update it. And let's try and do that now. So the update rules that we are going to follow are as follows. Let me write them down here. I W new is going to be equal to I W old plus E of I P E sub I. So let's write that clearly, E sub I P, and the value for the bias B of I new is equal to B of I old plus E of I. And with this 2, the value for the Perceptron rule, that's for the individual row case, individual neuron. If we write it in the matrix notation, it would be this capital W new is equal to capital W old plus E, and then we have P transpose, and likewise for B new we have B old plus E. So this is the matrix notation we have, and in the first case right here we have sort of at the neuron level, individual neuron level, ith neuron we talk about. So to get through this particular exercise now, to calculate the optimal value of W to classify the 2 points in 3D, here is the step 1. So for step 1, we write the following. We have A, which is equal to hard limb, and here we have the value for W, that's the W matrix, dotted with P1, that's the data point we are using, plus B, that is going to be equal to hard limb, and the W matrix we have, it's 3D this time, we have three values, minus this 0.5 minus 1 minus 0.5, and then for P1 we have 1 minus 1 minus 1, and then we add the bias to it, we get 0.5. Through this we perform the calculation of the dot product hard limb, and this becomes 0.5 into 1 is 0.5 plus minus 1 into minus 1 is plus 1, plus minus 0.5 into minus 1 is again plus 0.5. Then we have the plus 0.5 from the bias after that. This gets us a value which would be positive, and so our A we already know it's going to be 1. This is 1 plus 1 2 plus zero point 0.5 is 0 plus 2.5, and so the A that we get is 1. So what we are saying is that this particular weight matrix incorrectly classifies the data point P1 as class 0 when the target incorrectly classifies as class 1 when the class is 0. And we see that here in the plot that we created, where if we use this weight matrix which is shown here by the gray dot, uh, then this is the decision boundary we get, or the hyperplane, and it the point lies on the point that we just looked at, P1, which is this red point. It gets classified as 1, as you see. It's in the direction of the weight matrix, and that's not really what we want. That is supposed to be in the negative class with where the A is 0. And so it's time to update the weight matrix, and so to do that, let's go back, and now we'll perform the step of updating the value for W. And as we have seen previously, this is what we'll do. The new W is going to be equal to the old W plus E times P transpose, and the old W that we have is, we already know what that is. It is 0.5 minus 1 minus 0.5 plus the value for E. Now the value for E in this case is going to be T minus A. The original class is 0, and the class that we calculated was 1, so T 0 minus 1 is minus 1. So the E that we have is minus 1 dot P, and the value for P, that is the transfer function, sorry, the value for the input that we used was of course 1 minus 1 minus 1. Here we are transposing it, and so we write it in a row form, 1 minus 1 minus 1. If we go through this calculation, this would be 0.5, then all the values on this side would be the opposite sign. So this is 0.5 minus 1, then we have minus 1, and this is minus minus plus 1, and then we have the last one which is minus 0.5 minus minus plus 1, and this then comes out to minus 0.5 0, and this is plus 0.5, and that is going to be our new value for W. So that is the W new that we have. Likewise, we can calculate the value for bias. So the bias new is equal to the bias old plus the value of E. The older bias was 0.5. The new bias is going to be 0.5 minus 1, because E is minus 1. That gets us a value of minus 0.5, which is the new value for bias we have. So we box these two values, this one and this one. So in the step number 2, we are going to use these values, and the data point this time we'll use is the other one, the P2 one, the blue one. So let's do that. A is equal to hard limb. This is W dot P2 plus B, and here we have the value hard limb, and the W we have is minus 0.5 0 0.5, and the P2 is uh, P2 is, let's go back up and look, 1 1 minus 1, so let's write that down. 1 1 minus 1 plus b. B is this time minus 0.5. With this, we come back here, it's a hard limb. This is going to be minus 0.5 times 1 is minus 0.5, and then we have 0 times uh, 0 times, so that's what, 0 times 1 is 0, so let's put that 0 there, plus 0.5 times minus 1 is minus 0.5, so let me just erase that plus 1, type a minus instead, 0.5, and then we have the other minus 0.5 there. We now add all of these, and so what we get is hard limb, and this is going to be minus 1.5. Again, the value for a that we get here is 0 for the data point 1 1 minus 1, and the target class is actually 1. So we look at the error, e is equal to t minus a, the target class for that data point is 1, but what we get is 0, and so the error is 1 plus 1, and we use that to update the value for w. And so to do that, what we are going to do is the following: w new is equal to w old plus e times p transpose, and so the value for w old that we have is this one, the one that we just used, minus 0.5, 0, 0.5, and the value for e is simply plus 1, and times p transpose, the value for p is 1, 1, minus 1 that we just used, and so the new weight matrix would be minus 0.5 plus 1, that gets us 0.5, 0 plus 1 gets us 1, 0.5 minus 0 minus 1 gets us minus 0.5. And so this is the new w we have, w new, and again we can also calculate the new bias, which is simply going to be equal to the old bias. Then we can just add the value of e to this, and here the old bias is what, which is this one, the old bias b is minus 0.5, and we add plus 1 to it. So in the output we have plus 0.5 this time, so the bias is positive this time. Again we move on to the next step, so let's say this is step 3, and in the step number 3, we calculate the value of a is equal to hard limb, and again we work through this example. So let's say w, previously we used p2, so this time now we are going to use p1, so let's use that. W dot p1 plus b is equal to hard limb, and weight matrix is 0.5, 1 minus 0.5, the value for p1, which is the first data point, is 1 minus 1 minus 1. Let's write that down, 1 minus 1 minus 1, and the bias is positive 0.5. That's all we need, and then we simply do the dot product, where we have 0.5 times 1 is 0.5, 1 times minus 1 is minus 1, minus 0.5 times minus 1 is plus 0.5, plus 0.5 from the bias, and so these cancel out, what we are left with is hard limb, which is 0.5, and that gets us the value of a to be 1. Now, is that correct? Is that the correct class? Let's go up and find out. P1 is of class 0, and we got a class 1. So again, that does not meet the uh, that does not help us find the decision. That does not help. Uh, that does help get us the decision boundary. So we are moving closer to W, but it's not. We are not there yet. So we again calculate the error. The target was 0. We got a 1, and so the error E value this time is -1. So that's 0. Just confirming that. And again we calculate the values for W. So the W new is equal to W old plus E times P transpose, and W old is what? So W old that we just used was 0.51 minus 0.5 plus E, which is -1. And what is the value for the P? That value is 1 minus 1 minus 1, and so we put these calculations together. It says 0.5 minus 1 gets us minus 0.5, then we have 1, uh, and then minus minus plus 1. 1 plus 1 gets us 2, minus 0.5 plus 1 gets us 0.5. So the new weight matrix that we have is minus 0.5 to 0.5. Again, the new bias term that we have is simply going to be the old bias plus the value of E. The old bias is 0.5, and then value for E is -1. And so in this case, we now have a negative value for the bias. Hopefully, this will help us get closer to the correct weight matrix that leads us to the decision boundary that classifies the data points correctly. So we move on to the next step, and in the next step, which is step number 4, let me write that down on this page. Step number 4, we are going to say A is equal to hard limb, and this previously we used P1, so now we'll use P2. So W dot P2, and then we just add the bias term there. What we have is the new value for W. So hard limb, and the new value for W is minus 0.5 to 0.5, and the value for P2 is what? We go back up and just look at P2. It's 1 1 minus 1. So we scroll down and type 1 1 minus 1. It's important to not make mistakes while doing these calculations. So I try to focus as best as I can. 1 1 minus 1, and then we add the bias term, which is 0.5. So what do we get? Hard limb, and this is going to minus 0.5 minus times 1 is minus 0.5. So let me just write it out. Minus 0.5 plus 2 minus 0.5 plus 0.5, and so this cancels out. What we end up getting here is hard limb 1.5, and this brings us to A, which is the positive class. And looks like we have arrived at the final answer where uh, this class 1, so for P2, is correct. So P2 is target class is 1. We reached target class. So this in this case, then the error is equal to t minus a is equal to 1 minus 1 is equal to 0. So there is no error, and if you remember what we said earlier was that if there is no error, then the new w is simply equal to the old w. So the w new is simply going to be equal to w old, and there's no need to update the weight matrix further. And we can try and look at these planes here. So let's start with the very first case, where we have the random value for w 0 0.5 minus 1 minus 0.5. So 0.5 minus 1 minus 0.5, and this is the plane we get. And what we said at that time was that the p1 was incorrectly classified as class 1, and so p1 here is the red dot, and we can see that it's incorrectly classified as uh, positive, given that it is class 0. We then update the w. So w, after we use the new w, it's minus 0.50 0.5. When we use that w, the decision boundary then shifts. So that was the or the plane. Now the plane shifts to the here, and so in this case, we can see that in what we concluded here was that the P2 was classified as class 0, where in fact the P2 is class 1. So P2 in this case is the blue dot, which is classified as 0 because it's on the other side of the weight vector, and that does make sense. Then we move to the next case where we updated the w, and this time the w was this time the updated w was 0.5 1 minus 0.5. So 0.51 minus 0.5, and that got us this decision boundary or the hyperplane, which where we said that the p1 was incorrectly classified as 1, and so p1 in this case is the blue dot. It is on the side of the weight matrix and weight vector, which is classified as class 1, where in fact we said that the p1 had a target class of 0. So we went ahead and updated the w again, and this time with the new w that we have, we got a new hyperplane. So w was minus 0.5 to 0.5. That's what we have, minus 0.5 to 0.5, and that got us this hyperplane. And awesome, it looks like we did finally manage to uh, find the hyperplane with the optimal values of weight matrix w that correctly classify these two data points, and we can see them separated. The blue, which is the p2, which has the true class p2, as you can see it's 1, and it is class 1. We also see that here in the calculation for p2 we see that it's class 1 predicted, and that's also here in the plot, because that dot is in the same direction as this uh, this weight matrix that we have. And p1 and the other p1 is classified as negative because it's on the other side of the hyperplane, where the weight matrix is not weight vector is not pointing. So this is how we can think about when we train a neural network, is that we are moving the our decision boundary. So we are continually updating the value of w to find a decision boundary that allows us to classify the data points correctly. So for example, here again, this was our initial boundary, then we said, oh well, that doesn't work, then we kept found this boundary and that doesn't work, and so we finally ended finding a couple more, and that was the final decision boundary where we said, oh yes, that's the one that works. So the take home message from this lesson is that when we train a perceptron, what we do is we try to so when we train a perceptron, what we are trying to do is we update continually update the value of W. And how do we update the value of W? Based on the error. So how far we are from the target, and the error we use the value to update W. Again we find the error, again we update the W, and that W and B, and that goes on until the error is 0. So if E is equal to 0, then we just stop there and say that whatever W we have is the final W, and so that W should be able to classify any new data points that we get. That was it for this video. I hope in this video you got a good idea about the inner workings of how the decision boundary moves with the weight matrix, how the bias is updated, how weight matrix is updated in each iteration when we train a perceptron. Here we tried just a single neuron with two inputs, but it will apply the same logic will apply to more number of neurons and with a higher number of inputs as well. If you have any questions, comments, or suggestions, please do let me know in the comment section below. In the next video, we'll look at the proof of convergence. Bye for now.